What's up, AP Physics people? All right, so let's do some review. So we're gonna review forces. Forces, there's a lot going on in this unit, so we're just gonna pinpoint some key things here. Um, so the big one, when you think forces, you should think of F equals ma, and we're gonna have static, meaning at rest, and dynamic, meaning that it has some certain acceleration. We're going to look at F equals ma. To do that, we're going to look at, we're going to have to talk about like all these different types of forces, and then we're going to show some free body diagrams. Okay, so let's first talk about F equals ma. All right, Newton's second law. I need to be a little bit more specific here. So really, it is the sum of my forces. Forces are vectors. Acceleration is a vector. So when I say F equals ma, I really mean the sum of my forces. So let's look at these two cases. We have static and we have dynamic. Okay, so in the static sense, my sum of my forces, well, if I have my forces are all static, that means that I'm not accelerating, and that means that I'm at sum of my forces is 0. In this case, my sum of my forces, I am accelerating, so I'm going to have some sort of acceleration. I can think of it, I can rearrange it like this. If I'm trying to solve for my acceleration, it's my sum of my forces divided by mass. Okay, so let's look at an example here. For statics, a lot of times we have something that will look like this. So we'll have something that's hanging, and it will have a force on it. So we're going to talk about a force here. So we're going to have, and then we're going to talk about that force of gravity is equal to mg. But then we have two forces up here too. We have a tension force going here, so I'm going to call that T1. And we're going to have a tension force here, so we can call that T2. And we're going to look at this and we're going to say the sum of the forces is equal to 0. But I got to break this up. So for statics is a little bit complicated because I'm going to break this up into two parts. I'm going to say the sum of my f of x, my x components, and the sum of my f of y components are both going to be equal to 0. All right, this is just a quick review on looking at components of a vector here. So components of a vector, let's look at my y components here. So let's say that I give this an angle of 30, or let's give this one an angle of 40, and this one an angle of, it looks less, so 30. Okay, and those are degrees. So if I'm summing my forces in the x direction for this specific one, in the x direction, I'm going to have a negative T1 because it's going to the left, so I would have a negative T1. But I only want the component here that is adjacent to the angle. So a little trick here, if this is 40 degrees, this is also 40 degrees. So in this case, for this x component, since it's my adjacent side, I would have T1 cosine of 40 degrees. And then over here, I would have positive, because it's going to the right, T2, again cosine, of 30 degrees. And that would be equal to 0. Over here now, for my sum of my f of y, now let's look at, now I have one more force here. So I have the weight. So let's start off with that one. So I'm going to have negative mg. but my two y components now are positive. So let's look at T1. T1, this is opposite side, so I would have T1 sine of 40 plus T2 sine, and this one's 30 degrees. It's equal to 0. Okay, so now if they gave you like one of the tensions, or if they gave you the mass, you would be able to solve for a couple unknowns. So that's an example of a statics problem. Let's look at an example now of a dynamic problem. So let's do one first that's not at an angle. So let's say that we have this force, and we're applying a force, we'll call it F1 this direction. And we're going to talk about friction in a second here, but let's say that frictional force of friction is preventing this box from sliding. So I'm pushing it with some F1 and it has some frictional force. Okay, now in this case, I'm going to sum my forces, and I could put in the x direction, and I'm going to set it equal to, well, here if I have a net force, that means that it's going to accelerate. Whenever if these forces don't cancel each other out, it's going to accelerate. So I'm going to have mass times acceleration. All right. So in this case, the sum of my forces, I would have F1 minus FF, and that's equal to mass times acceleration. Okay, let's look at an angle here, because angles make things a bit harder. So now if I had something at an angle, and let's say it was accelerating. So let's put this at an angle here. So now I have, in this case, I have a mass, like a force going down. So I'm just going to call that mg. Though we're going to talk about types of forces here in a second, but let's say that I have a, this surface right here is pushing on it. So we're going to call that normal force, and we'll review that in a second. And let's say that I have a, let's say I have a frictional force, FF. So this is a rough board. Okay, now again, I'm going to come over here and use all this space. So I'm going to sum my forces in the x direction, and I'm going to sum my forces in the y direction. Okay, so a trick here though is if you look at this, here we have two forces that are at an angle, and this one's not at an angle. So here's the trick. So I'm going to, instead of writing it like that, I'm going to transfer this thing. I'm going to shift this down, so you can think of like, oh, I'm shifting this down. Well, if I shift that down, that shifts the weight down at that same angle. So at that same angle. I'm going to draw that over here because it looks pretty crowded over there. So one more time, I'm going to shift it down. And so if you look at that, that shifts the weight now. I'm shifting this whole thing. So now it's down. So this is the angle now. Okay, now my normal force is pointing straight up. The force at the surface is pushing on it. And the frictional force is just going straight to the right. So that's what we call that big F frictional force. Okay, now I can sum my forces. So in this case, I'm going to sum my forces in the x direction and see how it will have a let's say that this thing is moving. If this thing was moving down, it's going to have a acceleration. So in the x direction, let's say that has an acceleration, but in the y direction, it's not flying up off of this surface. So in that case, it would be 0. Okay, so if I sum my forces in the x direction, so let's do that. Sum my forces in the x direction. Well, I have this force here in the x direction, this component of my mass, or of my weight, sorry. So this component of my weight, so I'm going to have, it's going to the left, so I'm going to call it negative mg sine of my angle. And it's sine because you can see how it's opposite. It's opposite, so I have this negative one. And then I'm going to have plus my frictional force, and I'm going to set that one equal to mass times acceleration. So this is my x direction. So this is the sum of my forces in the x direction. So I'm summing my two forces. All right, if I do that in my y direction now, if I sum my forces in the y direction, now I have this positive Fn, I have my positive normal force, and I have here, I have this component of my mg, and it's going down, so I'm going to say negative mg, and this is the adjacent side, so I'm going to have cosine of theta, and that is equal to 0. My y direction is not flying up off the surface or anything, so that's 0. Okay, some complicated math here, and like restructuring of formulas, but I just want to give you guys the idea of this is how things are set up. Okay, so next thing, I had a couple type of forces here, but let's just review on types of forces. So types of forces. Okay, biggest one that you guys should think about, like, oh, what's one of the main forces? And we're gonna say the force of gravity, also known as something's weight. The force of gravity. And to give that an equation, we have F equals ma. So that's something that would be weight of something. Okay, we also have the frictional force. Frictional force. So the frictional force is given. We also have for frictional force, we have an equation of F is equal to mu times the normal force. Okay, I'm going to expand on that, but I just introduced another force here. So let's say this was friction. And we have the normal force, F of n, normal force. So we have F of n. And let's talk about what F of n is. That is the force applied to an object by the surface. So whenever something's on a surface, it's going to have a normal force. And it's always perpendicular. I'm just going to use this as the perpendicular sign. Or I'll write it out. Perpendicular to the surface. Okay, so that is a normal force. Okay, so up here, Fg is equal to mass times acceleration. Here I kind of made a little mistake. It's not a mistake, it is equal to mass times acceleration. But in this case, our acceleration is due to gravity. So that gravity is 9.8 meters a second squared. And for AP Physics, though, we use 10 meters a second squared. Okay, that's the force of gravity. Force of friction. So let's look at the force of friction here. So we got force of gravity, force of friction. Well, friction, this mu is the it's the coefficient of friction for a surface. So coefficient of friction for surfaces. So one thing is it is unitless, and its mu is in between 0, and I guess it can equal to 1. So it's this coefficient is in between 0 and 1, and it's saying like how rough or how much friction is actually in a surface. So if we had something like rubber with the two surfaces, rubber and rubber, we're looking at something that is close to 1. If we're looking at, let's say, ice and metal, those things slide over each other pretty well. So we're looking at something that is close to 0. Won't be absolutely 0 because that would mean that it was frictionless, but we're going to say like equivalent, like it's almost frictionless. All right, and that says that's mu, and then my normal force is that force from the surface of something. Okay, that's a quick review of the frictional force, and we got normal force. All right, I'm going to draw a couple things for normal force right here. Well, actually, we can get into that for this next page here. So let's talk about free body diagrams. Okay, so I'm going to need to know the type of forces to put on this free body diagram. So let's have a certain scenario. So free body diagram, let's say that I'm pushing a box. I'm pushing a box up a surface and it's at an angle here. Okay, so if I push this mass, a lot of times when we push it, we just call it an applied force. So I'm applying a force. If there is friction here, I'm going to have my force of friction. The normal force. Remember, the normal force always goes perpendicular to the surface. So there's my normal force. And I'm going to have a weight here pulling it down, which is mg. Okay, there's that scenario. So for a free body diagram. All right, let's do, sometimes on the AP Physics test, they have you draw, let's do an example of someone walking. They have you draw the forces at the point where they're acting. So a lot of times it will say something like this: where's the forces and where are they acting? And I just actually did something wrong here. So let's say someone is walking forward, and we're drawing the free body diagram for this person. Now here's something that's kind of funny. You might think like, oh, the friction is always acting opposite of the direction you're going. But if I look at this person here, well, what pushes you forward? So if this is for the free body diagram for the person, the force of friction on the person is actually going forward. So if I said like to draw the forces where they act, the force of friction is actually on at where the foot is contacting to the surface. You might think like, wait a minute, that doesn't make sense. Well, remember that forces come in pairs. So this force is the force of the foot on the surface. So here, like this is if I'm not drawing it. If I'm just drawing the person, or if I'm drawing the forces where they act, then I can draw something like that. Okay, let me think of another scenario. Okay, let's do this scenario. So let's say that we have an object falling with no air resistance. So if it's falling, it's only gonna have one force on it, and that's mg. If there was air resistance, we would have something like this. So force of air resistance. Okay, this was just a really quick review. So we're obviously going to start doing some problems with it, but I thought I would show you guys this review before we jump into any of the harder problems. Okay, hope this helps.